Yeah, kusekwa your boy. You see? Huh? Okay, so I'm just going for wave optics for Form 5 and Form 6. As you know, we have the wave optics, wave optics. We're just going to deal with the four things here. So what's about the wave optics before I just move to any step? Talking about the wave optics is actually the start of the optical phenomena, but on the wave nature of light. So it studied the optical phenomena, actually like diffraction, interference, polarization. We just studied those phenomena, optical phenomena, but in terms of wave nature of light. Light has different natures. That's why there are different theories like dual nature, that we believe that light has particle and wave nature. Also, there was Maxwell's and Hales who did the electrical experiments and came to prove that light is just the electromagnetic waves. There are theories like from Huygens. Huygens believed that it was a longitudinal wave which travels as the ether. So light has different waves, but talking about the have different natures. But talking about the wave optics, actually talking about the wave optics, we mean we study the nature, the optical phenomena, but depending on the wave nature of light. So here we focus on the study of optical phenomena, phenomenon, based on the wave nature of light. Actually talking about the nature of light, what are the optical phenomena? There are it still having the this definition still have some terminology. So speaking about the optical phenomena, the wave nature of light, optical phenomena, optical phenomena, optical phenomena. Some of optical phenomena are like diffraction. We can start diffraction. We can start about polarization. We can start about things like polarization, interference. So there are practical cases like, for example, in interference, why the fringes formation in soap bubble. When you look on the soap bubble, there are different colors that can be formed depending on the position that you are. So formation of colors, those are interference cases. Formation of colors by a soap bubble. For example, in polarization, my one like this now. When you look, it reduces the intensity of light because it's made up of polarizoids. These are polarizoids. So those polarization, will start about the polarization, those which pilots tend to wear when passing the sun rays. Diffraction cases like this, we say polarizoids. Diffraction cases are like you hear the sound around the corner or passing an obstacle, but you can't find the light just penetrating, just diffracting. No, light cannot diffract. So those cases why the sound can be diffracted but light can't be diffracted about the optical phenomena. But what's the nature of light? There are different theories explaining about the nature of light. Nature of light. Hey, take it easy and relax. Light is not only the electromagnetic wave. It have different nature depending on the different theories. So I have just some examples of theories that explains about the nature of light. And the nature of light depends on the theories. 5 theories. Let me explain about theories. The nature of light. There are some scientists like Maxwell's electromagnetic theory. This explains that light. These are just theories that explains the nature of light. It's explained that light is electromagnetic. electromagnetic wave. And this theory was proposed by Maxwell's, which he said that the speed of that electromagnetic of that light will just be equal to 1 over the inverse of the square root of E naught mu naught. But this is the permeability, this is the permittivity. So the permittivity, this is permittivity and this is permeability. Okay. So let's speak about the number 2. Let's say about the dual nature of light. So light also can be is just explained as it can be light can be particle or wave has two nature. So this theory explain about that light has the two nature. The third thing is about the Huygens. Huygens also. Huygens theory. He also explained that light is a longitudinal wave. He said that light is a longitudinal wave. Light is just a longitudinal wave. Just tends to move in a medium called the ether. It's not an organic ether that you know. Ether and not ether. It's not an organic ether. So light is a longitudinal wave traveling in the medium called the ether. So Huygens believed that light is just a longitudinal wave traveling in a medium called ether, and he didn't prove the presence of ether as light travels. So he came with some issues that called the wavefront. That layer of the surface of the path of light in which it flows, because he believed it was a longitudinal wave having a certain medium to pass through. But he didn't show. So Huygens actually he didn't show. Huygens didn't show. Didn't prove the presence of ether. But he contributed something very important. He spoke about wavefronts on the ether, on the medium which he called the ether. He said the light, this Huygens, he said that whenever light travels to a certain direction with a certain velocity, always it is the presence of that ether which is made of the wavefront. So on each wavefront, every point on the wavefront tends to act as the secondary source of the centenary wavelets, of the centenary wavelets, which tends to move in the same direction as the direction of the wave. This is the direction of the wave, of the wave. So finally, the next wavefront of the medium in which light passes also tends to have every point on the surface of that secondary wavefront tends to be the source of the other wavefront, by forming a certain wavelet. So every wavelet becomes the source of the next wavefront, which also tends to move in the same direction as the primary. So this is called the Huygens principle. Huygens principle. So what does it state? It says that every point on the wavefront tends to act as the secondary, as the source, of the secondary wavelets, which tends to move in the same direction, which tends to move to move in the same direction, in the same direction as that of the wave. And the net effect of the wavefront becomes the next wavefront. So the summation. So the effect of the secondary wavelet, the secondary wavelet becomes the secondary wavefront. So he speaks that every point on the primary wavefront acts as a source of the secondary wavefronts. That's what he speaks. So what the Huygens theory actually bases on the principle that light is a longitudinal wave traveling in the medium called ether, and not that it's not an organic ether that you know. He just assumed a certain medium, which he didn't prove about it. So the other method, the other theory explaining about the nature of light, the other theory. Let's discuss about the other theory. So we discussed about the electromagnetic theory. We discussed about electromagnetic theory was by Maxwell, also became proved by somebody called Hess, who did Hess by 1886. 186. So he proved this theory by electrical methods that the real speed of light was this one, which is equal to 3 times 10 exponent 80 meter per second. The dual nature of light, that light tends to have the particle and the wave nature, but also the Huygens theory, those tends to explain about the nature of light. Okay. Also Newton's explained, further Newton's also, number 4, let's discuss about Newton's. Newton's explained the nature of light as the corpuscles that can be emitted by any luminous object. So Newton's corpuscular law, theory of light. Newton's corpuscular theory of light. So Newton's also explained about the nature of light by saying that light. Let me use this. Light is continuous corpuscles. Continuous corpuscles coming emitted by a luminous object. So Newton's believe that luminous objects tend to emit some particles, which are called the corpuscles. That's why it's called Newton's corpuscular law theory about the nature of light. Okay, those about the theories, just explaining the nature of light. That's what we are going to start about the wave optics. It's about the study of the optical phenomena, but specifically based on this theory only, not other theories as I have done. Okay, so let's speak about the objectives that we are going to discuss about the wave optics. So as a student, when you finish studying about the wave optics, what should you know, so that we may say you are perfect on wave optics? The objectives, we call them the learning objectives. Learning objectives. Let's speak about the learning objectives, guys. Let's speak about the learning objectives. Okay. So specifically, let's speaking about the learning objective. Learning objectives. Objectives. Learning objectives. Objectives. Okay, let's speak about this. We have the 3 objectives that you need to know as a Form 5 student. The one is about the diffraction. Diffraction. You need to know about diffraction, my man. You need to know about the interference of light, and you need to know exactly about the polarization. Polarization. Okay, let's fuck the rest. So speaking about the interference, I'm just going to start with the interference. The first one is about the interference. Interference. of light, interference of light. Okay, specifically, I know you know about this, you know about the phenomena, but here you just need to know about three basic things. The first thing about the interference that you need to know about the basic concept, just the basic concepts about the interference. What does the interference mean? What are the types of interference? What are the conditions that whenever the waves superpose, we can form the interference, the observable one? You can interfere, but you cannot. Sometimes you can form the unobservable interference. So there are conditions, the types, actually the fringe patterns, or about those things. So the basic concepts, you need to know about the basic concepts about the interference. Okay, and these concepts, what are they? So you need to know about actually the types of interference. You need to know about what is the cause. The basic cause for the interference. Okay, you need to know about things like you need to know about types. You need to know about the conditions. You need to know about the methods on how we can achieve the coherence. This is about the superposition. You need to know about number 2, which is about the Young's modulus. Young's modulus experiment. And here on Young's modulus experiment, you need to know about the things like you need to know how to demonstrate the experiment. Actually, demonstrate, and then after demonstrating, you need to know about the formation of the fringe. So the appearance of the fringe, appearances of the fringes, but specifically also there are some cases that you need to know how to find the separation of those fringes, but specifically when you are given the angle of the interfering angle of interfering waves. The second thing you need to know when the eccentric glass is just pressed on the other side of the fringe, of just the slit. So the glass pressed or on one slit. You need to know also the alternatives of the Young's double slit experiment. Alternatives, we have for example, the Fresnel by prism, and we have a Leroyd's single, we call Leroyd's experiment, XP. Okay. So we're just going to discuss about those 4 things on Young's double slit. Also, the other concept that we need to cover here, we discuss about the thin film interference. This is about the formation of the soft colors. It's about the air wedge, the Newton's ring. So we need to know about the thin film interference. Interference. Okay, let me speak with you about the thin film interference. What are we just going to discuss here? So we're just going to discuss about the Newton's ring. So we're just going to discuss about things like air wedge. We're just going to discuss about things like we can say about the colors formed by the fringes. Colors on thin film. Oh my man, let me not forget about the blooming of the lens. Why the lenses tends to look bluish in color. So blooming of the lens, blooming of the lens. So those are the things that we are just going to cover here. Okay. So let me start here. About the basic terms here. Let me not forget about the basic terms. Okay, these are just the objectives that we're just going to start. So I'm just going to start one after another. Okay, let's go. Let's start here. Talking about the types of interference, you know exactly. I know from 6 students you just understand about the types. So speaking about the types of interference, as you studied in mechanical wave, you studied about the interference, the superposition principle. You did it. You calculated about those questions. So I just remind you about the types. We have the constructive and we have the destructive. Speaking about the constructive, constructive interference, and we have the destructive interference. Speaking about the constructive interference, what does it mean? It means that when the two waves meet at a point, moving in the same direction, but the specific condition for the formation of the constructive interference, they should be in phase. So whenever they are in crest, the other also should be in crest. Whenever they are in trough, the other also should be in trough. So speaking about the type of the constructive, we say it's a type just of interference in which the two interfering waves are in phase. But speaking about in phase, meaning whenever it's in crest, it's also in crest. So these two waves A and B, whenever they meet at a point, that is called the constructive. But speaking about the destructive, what does it mean? When two interfering waves are not in phase, they are out of phase. So those two waves becomes destructive. Destructive, saying out of phase. But speaking about constructive, they are in phase. Two interfering waves are in phase. Hey, what happens here to the intensities of light? Speaking about the constructive, the light becomes so brighter. So here it's about the brightness, the bright fringes. But here, the destructive, they reduce the intensity. But here there is the increase in intensity. That's what happens, my man. That's what happens. Hey, let me show you something. Very important to understand this. Speaking about the constructive interference, there are basic terms that you need to know about the wave. Speaking about the wave optics, one of the basic terms. Let me discuss with you terms before I just come to the types. Speaking about this, we have just discussed about the types. Let's speak about the terms. One of the basic terms that you need to know is about the path that the wave has traveled. So we have the path difference. We have a fringe and we have a phase difference. The fourth one, which we discussed on Huygens theory, was the wavefront. If you understand about these four basic terms, you are over about the wave optics. Nothing can disrupt you. One of the biggest problems that I just encountered to students, whenever a student fails, it's because of the two reasons. The first, he doesn't understand. The second, he has just forgotten about the concept. So if you understand this, it will make you easy to remember, to understand fast. Whenever you understand, it's not easy for you to forget. So speaking actually about the path difference is the distance that the wave has traveled. For example, if I speak about the path difference, the distance that this is the source A and this is B. These are the two sources of the two waves, but they are coming to interact or to interfere, to superpose at point P. So this wave travels this distance and this wave travels this distance. Oh, let me make it far. So let me move this point B to somewhere here. Let me say point B is here. Like that. So if the wave is moving like this to this point, while this one moves this point, so we say wave AP, its length from its source to a point of interference, point of interference. So we say this one has just moved 1 and 2, so it is 2 wavelengths. So wave AP is just equal to 2 wavelengths. But speaking about BP, this is about just 1 wavelength. So speaking about the path taken by the wave are these ones. But speaking about the path difference, it's the difference between the path traveled by the waves from their point sources to a point where they interfere. So the path difference now, path difference will just be 2 wavelength minus wavelength. So the path difference between AP and the BP is equal to just 1 wavelength. That's what we call the path difference, motherfuckers. So let's speak about the phase difference. Speaking about the phase difference is now the difference in the angular displacement of the two waves. So as the wave travels, it tends to change its angular displacement from the source. For example, as it starts from here, this side, as it moves, that's complete one cycle like this. So it moves until it comes here. But this one moves just one cycle and one cycle. Do you see the half cycle? So it forms just one cycle. So the difference in angular displacement of the wave is what we can say the phase difference. I know you learned about it in mechanical wave, so there is no so speaking about the phase difference, I think there is no problem. So this one can be either in phase or can be out of phase. So speaking about the phase difference, the difference in angular displacement, how much is the wave has been displaced in comparison to the other. So for example, let me discuss with you about this in deep, leading deep. So speaking about this, for example, if I say the phase difference is 90. So if this wave, for example, this wave here, so if I say this wave, when the difference, when it reaches its minimum, this one still it has exceeded its minimum and it has just started to rise. So they have a certain difference because this counts here 0, while this one counts a certain value of angular displacement. So this wave is leading this wave. Why? Because this one always arrives to the trough before this one arrives to the trough. So this means they have a certain phase difference, the certain angle of difference. That's what we speak about the phase difference. It's symboled like that. So specifically, let me show you just the common phase difference. For example, if these two waves, this one travels like that, and the other one, let's say, starts like that. This means this one is at the peak, as this one is at the minimum. So they have the phase difference of 90 because the other one is at the peak, while the other one is just on the start. So speaking about that, they have the phase difference of 90. Okay. So if we consider that this is wave 1, y1, and this is wave 2, so we can just say y1 is just equal to, let's say, a sine of wt, but plus who? Pi over 2. That's how they relate with the y2. Okay, so let me speak, while the y1, now this is y1, so speaking about the y2, we can just say now a sine of who? Of wt. You get that? So we can just start now about the wave front. Wave front. What's about the wave front? So we have just discussed about the basic terms. So we did about the types, the basic terms. So what are the fringes now? What are the fringes? Speaking about interference, whenever the two waves interferes, there is a formation of colors. And those colors are what we say the fringes. So speaking actually about the fringes, when you hear about the fringes, what are the fringes in wave optics? Fringes. Speaking about the fringes, we just say this is the band of wavelengths that are being formed due to the interference of the wave. So it's the band. Is the band of colors. Formed after two waves interferes. So these fringes are just the band of colors that can be formed. You see a soap or a centennial glass on air. When you press it, a thin glass on air, you just find some colors being formed depending on the on your position of the eye or on the soap bubble. You just find some colors like in air. So when pressing air, that's what we call the fringe, the bands of colors that can be formed when the two waves interferes. Okay, let's speak about the conditions for the formation of observable interference. Let's speak about the conditions. Those are, chief, Those are the introduction concepts before you do anything in interference. Before you do anything in interference, you need to know about those basic concepts. You need to know about the types as we have discussed in the basic terms, the three basic terms as I've told you. You need to know about the fringes, actually the carabands. You need to know about the phase difference. You need to know about the phase angle. And so you just need to know about the path difference. Those are the basic things, chief, before you move anywhere. So the third thing that you need to know is about the conditions. Conditions for the observable interference. So speak about this. Let's speak about the conditions for the observer. It's not that every superposition of the wave can result. Not that. It's not every superposition of the wave can result into the formation of interference bands. The fringes, no. The fringes are only formed, are only observed under these conditions. The first conditions, first condition for the observable interference. The first thing, it is something that we need to discuss here. Okay, I'll just continue with it. So speaking about the interference, the observable interference, the first thing you need to consider the sources. If the two sources, for example, this is the source and this is source A and this is source B. So emitting some lights. So the light goes and meets here to point P. Moves and meets at point P like that. So we have the source A and the source B. The first condition, these sources should be coherent sources. Okay. So speaking about this, we need to say sources should be coherent. What does coherence mean? This means the light emitted by these two sources, specifically guys, should have the same wavelength, same frequency, same amplitude, and comparable intensity. So speaking about this, we need to have the same wavelength, amplitude, frequency, but with what? A comparable intensity. But speaking about the amplitude, we can just mean the intensity, because they are larger the amplitude, the larger the intensity. So speaking about this, intensity, comparable, intensity. But also, the fourth thing that you need to know, the phase constant, phase difference should be constant. If one wave exceeds the other by 90, should be by 90 forever until they interfere from their sources. So speaking about this, the phase difference should not vary, guys. Should not vary. This means the medium should be isotropic. The isotropic medium, this means as the wave travels through the medium, its speed is just constant. So it doesn't change. So speaking about the phase difference should be constant. Should be constant. That's what means by the coherent sources. The sources should be coherent, meaning they should have the same amplitude, frequency, wavelength. The phase differences should also be constant. That's what we say. The second thing that we need to know, we need to know that the sources should be close to each other. If the one source is so far from the other, now the interference won't happen exactly. So the sources, my guys, sources should be close to each other. So the sources should be close to each other. If they are not so close, meaning they can't now interfere. The third thing for the interference to occur, they should interfere. There must be a point where they meet, either on the screen or the eyepiece of the eye or the eyepiece of the microscope. So there should be a point where they should interfere. So that's why we call it interference. So we say the two waves should meet at a point. Two waves should meet at a point. That's what will happen. Okay. That's about the sources. Yeah. Speaking about also the we can say about the other thing that we can say, we can just see about we have just spoken about the coherence, actually the coherence nature. We've just spoken about the closeness of the waves. We have spoken about the meeting, but also the wavelength. The wavelength should be monochromatic. It should not be the band, for example, just the white light. If it's a white light, now the fringes will just separate themselves. So we just say it should be a monochromatic light. A monochromatic light. Wavelength. Should have one wavelength. So the light rays interfering should be monochromatic. Chromatic. Hey, and also the source should not just be like should be not just beeping. Should be continuous sources of light. So the sources of light, actually the other sources of light, sources of light should emit light continuously. So if they emit just the point light, so they just emit and cut off. That's, you can't observe now that interference, because the one will just reach first before the other, depending on the coherency source. Okay. So how do we achieve coherence? Because it's like light is just the same, but we know the formation of light, it just depends on the source. So whether it's so far or it's just we say its intensity, that's why it depends. For example, you can have the two torches from just one car, but they cannot be coherent. So there are special methods that we can achieve coherence from just one source. We obtain the two sources, but coming from the same source, so that we can have the same wavelength, same frequency, same phase constant, the constant phase constant. That's what we speak about the coherence. How the methods, how can we achieve coherence? The methods on how we can achieve coherence. Those are the basic concepts of interference. Okay, let's speak about the methods on how to achieve the coherence. Methods on how we can achieve the coherence. Methods on how we can achieve coherence. Okay, let's speak about the methods. Let's speak about the methods. Methods of achieving coherence. Okay, let me speak about with you. So about this, we can have the wavefront division, division of wavefront, division of what? Wavefront. But the second thing is about the division of the amplitude, division of amplitude. Okay, well, how does it occur, man? What are they? So speaking about the coherence now, the coherence can be achieved by division of wavelength. We just use one source which emits the light to the two slits, which tends to remit a part of light and allow just a part of light to pass through the two slits. So passing through the two slits, since they have just come from just one common source, they have the common wavelength, same amplitude, same intensities, so they are just coherent. So speaking about the wavefront, speaking about the division of wavefront now, it's when one source, for example, this one is the source of light, allows to pass. This is slit A and this is slit B. So the light is allowed to pass here. So the light coming out from here, this is an obstacle. For example, this can just be a card that has been pinched off with the hose. So this is a card just pinched off with the hose. For example, if I take this card and pinch here, and then use the source of light here, so the only light that comes here, they are coherent sources. So these A and B are coherent, but by which means? By division of the wavefront, by division of wavefronting. So speaking about this is about the division of wavefront. So it's just it is when one source is used to form the two sources, two secondary sources. So this is just the primary source, while these are the secondary sources. So speaking about it is one source, use the two give two sources of light. Okay, speaking about the division of amplitude, by by, because achieving the coherence we should use one to obtain the two, but you need to specify by only dividing the wavefront. So the wavefront will just come like this, the wavefront. So here we just have the wavefront here will be limited by the obstacle and then divides themselves, and they start then they can just now start to move like that. So speaking about this, we can say by limiting the primary wavefront, with a pinched cardboard. So use the cardboard to limit the source of light, the primary source of light. That's what happens to the division of wavefront. But how about the division of amplitude? How can you divide the amplitude? How can you divide the amplitude, Madogo? How can you divide the amplitude? Talk about the division of amplitude now. You just illuminate this. You take the source of light and illuminate it on the transparent surface, so such that it can be allowed to reflect and to transmit. So speaking about the division of amplitude, this is actually the method of achieving coherence, whereby light tends to be illuminated on the transparent medium and the part is being allowed to transmit and the other is being reflected. So this is reflected, while this one is transmitted. This is, let's say, this is the normal line here. So this is the reflected one, while this is the incident ray. So this one is incident ray. So what happens here? Just observe this. When the screen is here, this is the screen to observe now. Screen to observe. So when the incident light here, this is the primary source. This is the primary source. Primary source. How do you obtain the two coherent sources? By this method. So you just illuminate on the glass. Let's say glass, which is transparent now. A part is being transmitted and a part is being reflected. So on the screen, you just observe this, the reflected, as this source. So you just observe as you illuminate it on the transparent. You observe the two sources. The first thing, you just observe that source, and the second thing, if you are on the screen, you just observe the primary source that you use. So the primary source and the secondary source, the secondary source, which is the image of the primary, is now the two sources which are coherent. A and B are coherent. A and B are coherent, but by division of the amplitude. Why? Because the incident ray has been divided its intensity by 2. So the other one and the reflected one. So we say the incident ray has been divided its amplitude. That's why we say achieving coherence by division of amplitude of the wave. So there are two methods of achieving coherence. That, Chief, that is the good intraday. That is the good intraday. You can't say you know interference without knowing the terms like the phase difference, the path difference, the fringes. Chief, you can do nothing now. You can do nothing. You can't solve an equation without knowing the fringes in wave optics now. And just in case you don't know, that's the problem. There is where there is a problem. Student doesn't know about the fringes, the orders of the fringes. That's where the problem is. Actually, you need to know about the basic terms, and you need to know about the types. You need to really know about how can we achieve the coherence and the conditions for the observable interference. Okay, so those are the basic concepts. Let's move on to the Young's modulus experiment. Young's modulus experiment. Young's modulus experiment. Young's modulus experiment. Okay, let's speak about this. Young's modulus experiment. Young's modulus experiment. Let's speak about this, my man. So let me demonstrate it. What does it mean? This was the experiment Young did. Young's experiment. Young's modulus experimenting. Speaking about Young's modulus experiment, let's speak now about this. Let me demonstrate it. The first thing, actually, Young's used the wavefront, achieved the coherence by using the wavefront, division of wavefront. Now you know, my man, how we use. This is the source. Now, primary source S. Let's say source S. Source S. This is source S now. Tends to emit now light. But we have the slits here. Guys. So speaking about these slits now, light tend to form the wavefront. So the wavefronts like, but they are limited by the obstacle. So this is slit A and this is slit B. So this one also starts here, and this also starts here, and they finally interferes. So on the screen here, this is the screen. What happens? This central line continues to move up to the screen here. So this is the central line, central axis. So for example, this is the setup for the experiment. That you just take the source. For example, it's a torch. Then you take a cardboard that has the fringes. You have pinched the two O's, then which should be crossed, should be crossed as the condition for the formation of the observer, and then it should be the eyepiece or the screen or the microscope there forward, so as to obtain to see the interference pattern, which is now observed as the fringes. Okay, let's speak about the interference now. What does it mean? Let's speak about the measurements. The distance now. Let's take the distance from the slits to the screen. Let's call it D. The distance D, the capital D. Let's speak about the distance between these fringes. This is, let's say, distance A. Distance between the two fringes. Distance A. Let's speak about the fringes. The point where these two rays coming from this slit and this slit, they can interfere. A point where they can interfere. Let's say this point is the point of interference, point P. So speaking about that, let me now draw it well. This is the distance y from the central axis, the point where the two waves will interfere. Point of interference from the central axis. So what happens here? You can find this depending on those values. So look here, if we have this coming from here and this coming from here, so we can say this one, since it have just started so far before the other, so it have a certain path difference, which is this one. So we can say, let me draw it by using the nice here. Let me draw it well here. You can see it well. So if this is A and this is B, so we have B and this is the central axis. And so if we have this and this, so we can have N, for example, this is N, point N. Now this is the path difference between AP and BP. The path difference between BP minus AP This is the path difference. Path difference, which is actually BN, which is actually BN. So speaking about this, we can say this angle geometrically, this angle is just equal to this one. It's just equal to this one. So we can just say tan, for example, this tan of theta is just equal to opposite y over the adjacent, which is D. But also, you know, sine of theta, because this angle here is just equal to this geometrically. You know that because this is 90 and this is 90, so you can just make the comparison for the right angle side, the common line there. So speaking about that now, we can just now speak about the sine of this theta is just equal to Bn, which is this point B to N, and over this one, which is the distance from here to here. We have just said it. Let's call it A. So over A. So we can just say Bn, Bn over A is just equal, because the sine of angle is just approximately equal to tan if it's a small angle. So we can just say in comparison with y over b. So we can just see exactly that. Bny. So Bn times B over A. This is just equal to y. Now we can see exactly who is Bn. It's the path difference. What is the path difference? It's the difference in wavelength of the two waves it traveled. So the two waves interfering, the difference in their wavelength it traveled from their point source to the point where they interfere is what we call the path difference. So the path difference is actually the difference in wavelengths. So this is D over A equal to Y. So the difference in wavelength times D, that is the formula to obtain D. Where is these fringes are going to be formed exactly? That's what we speak about the Young's modulus. That's I have demonstrated about the formation, the point where the fringes will just be formed. Okay, let's speak about the appearance now. Appearance of those fringes on the screen. Appearance on the screen. Actually, the appearance will just depend on. So it's now the sun has just now set off. So I need to end here, and then I'll just come and continue with this part in the next phase. Okay, tomorrow I just start early as possible. See you guys. Today I just all my spectacles because it's wave optics, so I could just to make some optical phenomenon right now. Okay, I'm signing out. It's your boy kusekwa. Chill down, guys. Dang.